Welcome to the Crazy Hat Chemist. So today we're doing another video here. It is the third video in this series of covalent bonding. So today we're going to be doing which video? The covalent bonding worksheet number 3. And today's video is brought to you by the Crazy Hat Chemist, sponsored by the Crazy Hat Chemist and all things crazy. All right. Before you get started on this video, you need to be having a couple of items with you so that you can actually proceed on forward. And so that would be a periodic table. And in a previous video, I have already discussed the valence electrons, the electronegativities of certain elements. So in brief, the valence electrons go by the group, and that is the columns on the periodic table, group or family. So group number 1, 1 valence electron, group number 2, 2 valence electrons, group number 3, 4, 5, 6, 7, and 8. That would be 3, 4, 5, 6, 7, and 8 valence electrons, respectively. Fluorine is the most electronegative element there is, and francium would be the furthest, so it is the least electronegative. So you're going to have that periodic table at hand, close by. Also, you do need certainly this worksheet. And if you don't have one, then you should get one from me, and that is the covalent bonding worksheet handout number 2. And there is a video which describes this table right here, which is the molecular geometry, bond angle, and polarity, and especially the axe. You got to chop it up with that axe. That's right, folks. Okay. So, and where would you find that video? It's under the Crazy Hat Chemist if you follow that YouTube of me. And so let's zoom on in here. It's the Crazy Hat Chemist. It's the Honors Chemistry 6 playlist, the bonding collection, and video bonding number 28, calling molecular geometry. It goes over the axe, the molecular geometry, bond angle, and polarity, and much, much more for the same price. That's right. And also on this worksheet, the lower third is the following. And this is the sequential steps on how to draw Lewis dot structures. That is absolutely essential on what we are doing here today. And so where would you find information on how to draw Lewis dot structures? Well, you would look at the YouTube video from the Crazy Hat Chemist. That's me, yours truly. You're going to go to the Honors Chemistry 6 playlist, which is the bonding collection. You're going to look at the bonding number 11, Lewis dot structure rules video. And in there, I give the whole directions on how to use this. All right. And then before you actually start this video, of course, you need to have actually watched previously the covalent bonding worksheet number 1. And you need to watch the covalent bonding worksheet number 2 before you start number 3. That's essential. So today we are going to do covalent bonding worksheet number 3. So let's zoom into that worksheet and let's get moving. So let's see if I can zoom this on in for what we want. Again, this is the covalent bonding worksheet number 3. That's what we're doing today. So let's zoom on in here and see if we can hammer this out. This is going to be a great day, a great video, and many more to come. Absolutely. Okay. I'm here for all your chemistry needs here of learning real, awesome, great chemistry. That's why I'm here. Okay, so the first thing that we're going to do is we are going to do this first problem here, and that is hydrogen sulfide. So you can either look this up if you want to, or you can know how to come up with this formula. So hydrogen is a +1, sulfide is a 2 minus. You're going to take the absolute value of these two numbers, flip the numbers, and drop them down, and then you will get the formula of H2S. Hydrogen sulfide is a very, very smelly gas. It smells like rotten eggs. So if you've ever been to Yosemite or Yellowstone, then you would actually smell that. So now what we're going to do is we're going to look on our periodic table. We're going to find hydrogen, and hydrogen is right here. It is in group one, so one valence electron. So there's one valence electron, and there are two hydrogens. Then we're going to find sulfur, and sulfur is right here, and sulfur has six valence electrons. There is one sulfur, and it has six valence electrons. There's one sulfur, so that's two, that's six. I'm going to add those two numbers up. I'm going to get 8. And what do we always do? We always divide by 2. That's right. Always divide by 2. And that will get you the number of pairs of electrons. So there are 4 pairs of electrons that we have to deal with. All right. That is the first rule, and using those Lewis dot structures. Now, the next rule is to find the least electronegative element that will go in the center. Sorry about that bell right there. I forgot we are actually still at school. No way, no how. All right, so that's just a little bit of a wake-up call just to make sure that in case you were asleep, then now you're not. Certainly, at least I'm not anymore. So here we go. We'll have a couple more of those bells. Hopefully we can avoid those here before we get moving. So the Lewis dot structure, we need to find the least electronegative element. Again, we have summed up the total number of valence electrons. We're going to determine the central atom. It's the least electronegative element. However, it cannot be hydrogen. So we have either hydrogen or sulfur. So by default, it actually is going to be the sulfur. So I'm going to place the sulfur there right in the middle. Okay. And then we're going to draw the sign of a cross, a plus sign, or whatever you want to do. That is that right there. And now the other elements, of which there are hydrogens, will be surrounding this in this 3 o'clock, 6 o'clock, 9 o'clock, and 12 o'clock position. So I'm first going to be placing this hydrogen right here in the 3 o'clock position. Then the next position is the 6 o'clock position where the hydrogen goes. Excellent. Now what we need to do is we need to place the pairs of electrons that are bonding in between the central and outside element. Again, we're going to place the additional atoms in the faces of a clock like what we have done. Now we're going to place a pair of electrons between the central atom A and the surrounding atoms X. The central atom A is the sulfur. The surrounding atoms X are the H's. So I'm going to place a pair of electrons as a line in between the central and outside. Central and outside, that's a pair of electrons. Now I've used up 2 of my 4 pair. I have 2 pair yet remaining. If electron pairs remain, place a pair of electrons on the surrounding outside atoms, those are X's, as lone pairs or non-bonding pairs of electrons. So theoretically, what we would do is to do the following. We would place a pair of electrons here, and then maybe over here, or maybe even here. But I'm going to circle this hydrogen. And there are 2 rules that we are going to be following here. One of the rules is that hydrogen follows the duet rule. A duet is 2. And how many electrons are in this circle surrounding the hydrogen? Well, that's 2, 4, and 6. That's 6 electrons. That is a no way, I can't do that. So I'm going to erase these 2 electrons that are right here. And maybe I could have placed those electrons around this hydrogen and circled that one. So how many electrons can hydrogen have? 2. It's a duet. So in this circle at the 3 o'clock hydrogen position, I have 4 electrons. That's absolutely no way. You cannot do that. Same with this 6 o'clock hydrogen. This is a violation of the duet rule. So you cannot violate rules. So we're going to erase all of what I have done right there. Okay. And now you should see I'm back to just having a bonding pair of electrons between the central atom, sulfur, and the outside atom, hydrogen. The next rule, so I can't actually do this 3B rule, placing alone pairs on the outside elements. That's a violation of the duet rule. The next rule is if electron pairs remain, of which they do, place the remaining pairs of electrons on the central atom A as lone pairs or non-bonding electrons. These lone pairs of electrons on the central atom are designated as E. That is actually critical. Uh-oh, the train is coming. Watch out. Here it comes. All right, we're in the train station. So again, what we're going to do is we're going to place lone pairs of electrons on the central atom. That is going to go right here like this and right here like this. I have used up 4 pairs. That's 1, 2 as bonding pairs of electrons. I cannot place lone pairs on hydrogen because it follows the duet rule. And then there are lone pairs on that central sulfur atom, just like that. These are E's. Okay, you're doing a fantastic job. Now what we're going to do is verify the duet rule for hydrogen. I'm going to circle that. That's 2 electrons around that 3 o'clock hydrogen. The duet rule for this 6 o'clock hydrogen, that's 2 electrons. And then we have the octet rule for all other elements. And so around this sulfur, it must have an octet that is 2, 4, 6, and 8 electrons. That is absolutely correct. All right, sorry about that last little bell there. We were ready for the train. I let the train go through the station, but you don't want the other bell. All right, so that's hopefully looking good right there. And now what we need to do is we need to do the following. We need to come up with the molecular geometry or the shape, and this is all based on the axe. So we're going to draw out the axe, A-X-E. So what is the A? The A is the central element. In this case, it's the sulfur. That is an A. The X are the elements that are physically attached with bonding electrons with the central element there. So that would be the 2 hydrogens. So that would be AX2. Then E, for the very first time, we didn't come across an E in worksheet number 1 or worksheet number 2, but here it is in worksheet number 3, we have an E. E are the lone pairs of electrons on the central atom, and there's 1, 2 lone pairs. Remember, this is pairs. So now what we need to do is we need to look on our sheet of paper here, and we are going to find it. All right, so now what we need to do is figure out what AX2E2 represents. And so we're going to go to this little table right here, and we're going to go ax, we're going to find AX2E2. AX2E2. AX2E2, that would be angular or bent, and it has a bond angle of 105. And look at that, it says it's polar. There's not even a possibility of it being nonpolar. So AX2E2 is angular or bent. So I'm going to write the name angular, or I can write bent. It doesn't matter, one or the other. And like I said earlier from our little table here, if it's angular or bent, the bond angle is 105 degrees, 105 degrees. And the molecular polarity, well, really what we need to do is we need to be able to make the model, and I'll show you that in just a bit, but it is polar because it is asymmetrical, and that makes it polar. So depending on the model kit that you have, the sulfur, and by the way, I do have a key here for my model kit. Okay. The yellow 2-hole is representing the sulfur. The hydrogen is represented by a white one. Okay. And hopefully you have a model kit with something similar to this. If you don't, then you should pick one up and, try to pick it up from one of your local stores. Support local things as opposed to that online garbage. And maybe you need to go to the online garbage, but what can I say? So the sulfur is the yellow thing, and the hydrogens are the white things. The gray things are the bonding pairs of electrons. Now, this model here of sulfur does not have lone pairs of electrons, and so it depends on the model kit of which you have. I have different model kits and I have different ones. So here is another representation of this hydrogen sulfide. And right here, you should see that this one is similar to the one so I got the right-hand one, I got the left-hand one. The left-hand one is your basic model kit. You can see that it is bent. It is bent. This is a bond angle of 105 degrees right here. This is the bond angle of 105. There are assumed lone pairs on this. This model actually shows the lone pairs. So these two tan things are the lone pairs of electrons. The yellow is the sulfur. The white things are the hydrogens. And so I'm going to spin this around. You should see that this is hydrogen sulfide, and it is most certainly bent. Okay. The bond angle here in this is right here. This is the 105-degree bond angle. Just so that you know, if you want to know a little bit more, this bond angle here is actually compressed from what it normally would be because these lone pairs of electrons that I'm holding on to right now compress the bond angle, changing it from 109.5 to 105 because there are two lone pairs of electrons. That's an important point in a higher level of chemistry. So this is our Lewis dot structure and our model. This is our model on our basic kit for hydrogen sulfide. All right. Hopefully you've got that. Okay. All right. So now what we're going to do is we're going to move on. We're going to do the next one, and that is going to be ammonia. And if you don't know what ammonia is, then you should look it up online and figure out what ammonia is. You could actually probably look it up in your textbook as well. But you might even have a window cleaner that has ammonia in it, or you might be using ammonia in your bathroom for cleaning purposes. That could be too. But ammonia is a hydrogen, which is 1 plus, and a nitrogen, which is a 3 minus. So I'm going to take the absolute value of these two right here, flip the numbers, bring them down, and then I'm going to write it in its common form, which is NH3. So there it is, NH3. NH3. Sometimes I've seen it as H3N. That is possible also. Not a worry. So how many nitrogens are there? There's one nitrogen. How many valence electrons are in nitrogen? Well, nitrogen is right here. How many valence electrons in nitrogen? That would be 5. So there's one nitrogen at 5 valence electrons, one nitrogen. How many hydrogens? There are 3. How many valence electrons in hydrogen? Valence electrons in hydrogen would be 1. So 1 valence electron in hydrogen, there are 3. So I got 5, I got 3. I'm going to add them up, and I am going to get the magic number 8. And of course, the crazy hat chemist, he always works in pairs. I'm going to divide this by 2, and I'm going to get 4 pairs. 4 pairs of electrons. All right. Fantastic. This is a 3 here. Kind of looked almost like another number, not sure. All right, so now what we're going to do is we're going to find the least electronegative element, but never hydrogen goes in the middle. That's our central atom that we're looking for. So the least electronegative element is going to be hydrogen, but you cannot place hydrogen in the middle. So therefore, by default, it will be the nitrogen. And just like before, I have the sign of the cross, or I have a plus sign right here, and we're going to be working with that. And I'm going to be placing those hydrogens around that in the 3 o'clock position, the 6 o'clock position, and then the 9 o'clock position. Those are the 3 hydrogens in which I have. I'm going to erase that plus sign, and there we go. So the next set of rules or the first set of rules in placing electrons around this would be to write bonding pairs of electrons between the central A and the outside X, central A, outside X, central A, outside X. Those are bonding pairs of electrons. I've used up 2, 4, 6 electrons in total, or 3 pair. I have 1 more pair left over. The next rule is to place lone pairs on the outside atoms. And again, hydrogen follows the duet rule, so that would be a violation of the duet rule. So that would be wrong. That's a nope, don't do that. So then what I do is I place lone pairs of electrons on the central atom as lone pairs. Okay, I'm going to verify the duet rule. This 3 o'clock position of hydrogen has a duet. This 6 o'clock position of hydrogen has a duet. This 9 o'clock position of hydrogen has a duet. And this central atom of nitrogen has an octet. That's 2, 4, 6, and 8 electrons. Excuse me. So verify the octet rule and the duet rule respectively. I'm going to erase all this stuff right here because that really doesn't belong. And then this is my Lewis dot structure as is appropriate. All right, now what we're going to do is we're going to draw the axe. So the axe is as follows. That's AXE. The A is the central element. How many A's are there? There's one nitrogen, there's one central element, that's an A. How many X's are there? Those are the elements that are surrounding the N. And so there are X's, how many? 1, 2, and 3. So there are 3 X's. Are there any E's? The E's are the lone pairs on the central element, and there is one E, so that's an E. Now I need to come up with a name that corresponds to AX3E. So I'm going to pull out my handout again. It's essential that you have this handout. And so that would be the following. AX3E, that corresponds to trigonal pyramidal for a shape. I'm going to write that down. Trigonal pyramidal. Some people call it trigonal pyramidal, trigonal pyramidal, one and the same thing. Really doesn't matter. Now I'm going to come up with the bond angle. So the bond angle is also with the AX3E trigonal pyramidal at a 107 degrees. So that would be 107 degrees. And then, is this symmetrical or asymmetrical? Well, I can actually look on this sheet of paper here as well, and you can see that it is asymmetrical and leads to being a polar molecule. That's asymmetrical and polar. So now what we need to do is we need to build the model and verify that it is actually asymmetrical and polar. So the central nitrogen is this blue atom right here that you see in the middle. The hydrogens are the white things. I'm holding on to 2 of them. The gray things are the bonding pairs of electrons. And this tan little paddle thing right here, that's the lone pair of electrons on the central nitrogen. And so that you can see that this is asymmetrical. Like this side is different than that side, and it is polar. Really, what is polarity? Polarity is something that is asymmetrical. So you have to have bond dipoles. So there's a difference in electronegativity. The nitrogen is more electronegative than the hydrogen. So there's a bond dipole moving in that direction, and that direction. And then there's that lone pair of electrons, and that's negative. So the molecular dipole is actually this line that goes in that direction. And if you can have this asymmetry with a molecular dipole, that means that model or that molecule is polar and it's asymmetrical. So this is a polar asymmetrical molecule, and that is why. Hopefully you see that. Good representation of ammonia. All right, perfect. Let's move on to the next one here, and the next one is going to be water. So hopefully you understand what water is, and that formula is H2O. Hopefully you didn't need me to write that out for you, and hopefully you didn't need to look that up online. Ouch. All right, so we're going to count up the number of valence electrons in hydrogen. So valence electrons in hydrogen, 1. So valence electrons in hydrogen, there's 1 of them. How many hydrogens are there? There's 2 total hydrogens in this molecule. Valence electrons in oxygen, 6. So there are 6 valence electrons in oxygen, and there is 1 oxygen. So that's 1 times 2, and that's 6 times 1. I'm going to add those up. I get 8. And then, as always, the crazy hat chemist divides by 2 because he can't count that high. So he's going to be working with how many pair? That's correct. That is 4 pairs yet again. The least electronegative element goes in the middle, but never hydrogen, so we cannot place the hydrogen in the middle, so therefore we are defaulting to the oxygen going in the middle. And then we have the sign of the cross, or a plus sign right here. That's where our 3 o'clock, our 6 o'clock, our 9 o'clock, and 12 o'clock position atoms will be going. So we have a hydrogen in the 3 o'clock. We have a hydrogen in the 6 o'clock position. We're going to erase these dashed lines here as my basis, because we don't really need to put that there. Hopefully not. We are going to place our pairs of electrons according to the rule. So our four pairs of electrons, our first rule is place a bonding pair of electrons between the central A and the outside X. That is the central atom and the outside atom. Central atom and the outside atom, bonding pairs of electrons. I've used up two pairs of my four. I have two pairs yet remaining. My next rule is to place lone pairs on the outside atoms, and I cannot do that because hydrogen follows the duet rule, and I would violate the duet rule. So I'm going to go to the next rule. The next rule is to place lone pairs of electrons on the central atom, and that would be my two remaining pairs of electrons. I'm going to verify the duet rule. That is two electrons right there for hydrogen. The duet rule only applies to hydrogen. There's my two electrons. I'm going to verify the octet rule for all other elements, and that's 2, 4, 6, 8. That's an octet. So I have verified that. Perfecto. All right, now what we're going to do is we're going to come up with the X. It's AXE. The A is the central element that is represented by the oxygen. The X's are the atoms that are physically attached to that central element. That is that hydrogen at 3 o'clock, this hydrogen at 6 o'clock. There are two of those. The E's are the lone pairs of electrons only on the central atom, and that is 1, 2 lone pairs. So I'm going to look at my table here, and I'm going to find on my table, I'm going to find AX2E2. That's angular or bent, 105 degrees, and it's polar. That's right. So it is angular or bent. And that's 105 degrees, and it is asymmetrical. And I will show you that with a model, and therefore it's polar. So I'm going to show you a few different models here of the water, and hopefully this will work for you. A number of different models. So the oxygen is represented by the red, and the hydrogens are represented by the whites. The grays are the bonding pairs of electrons. So this model here does not have lone pairs of electrons on it. You should see that this is the bond angle right here of 105. Perfect. Our next model here, that is a possibility if you have the paddles and you have the correct number of spaces in that oxygen. The paddles here, the tan paddles, represent the lone pairs of electrons. That's another model of water. You should see still that it's a 105-degree angle and it's bent. Here's yet another model. Instead of the paddles, there are these tan little spheres. These tan spheres represent the lone pairs of electrons, and that is asymmetrical and bent as well, 105 degrees. And then finally, the last model here, I'll put that here. It's the tan lone pairs, and then these lobes that are gray are representing the bonding pairs of electrons. So depending on what model kit you have, you might have a better model kit or not as good a model kit. But it doesn't really matter because with any of the model kits, you can see that it's a bench-like structure and it is asymmetric. That is, there's a molecular dipole in this direction right here like that, and that makes this molecule asymmetrical and therefore polar. Okay? Any of these represent that quite well, truly. All right, hopefully that's good. I'm going to remove all of this here, and I'm going to scoop this all up. Voila, look at that. And then we're going to go to our next one. So I'm going to have to slide this worksheet up here a little bit. And this is a time for our advertisers to give a little bit of an advertisement and by our sponsors. And so our sponsor for today's video is none other than the Crazy Hat Chemist. That's right, folks. Crazy Hat Chemist is the sponsor for today's video. Thank you very much to the Crazy Hat Chemist. I'm right here. Yeah, okay, fantastic. The next one is silane, which is SiH4. So we're going to look on a periodic table and find silicone. Silicone is right there. It's underneath carbon. It has 4 valence electrons. So it has 4 valence electrons. There's one silica or one silicone. Hydrogen. We've done hydrogen for every one of the ones on here, but hydrogen has one valence electron, and there are four of them. So one valence electron, there are four of them. That's a four, that's a four. I'm going to add those up. That's eight. And as always, we're going to divide by two, and we get four pairs. The least electronegative element, but never hydrogen goes in the middle. So consequently, hydrogen doesn't go in the middle. So that means the silica or the silicone goes in the middle. And then sign of the cross or X marks the spot. That is the treasure for the pirate. And the hydrogens in the 3 o'clock, the 6 o'clock, the 9 o'clock, and the 12 o'clock positions go there. I'm going to erase the sign of the cross, the plus sign, the pirate's signal. And now we're going to place our four pairs of electrons as is appropriate. The pairs of electrons are placed between the central and the outside element as bonding pairs of electrons. That's one. Central and outside, that's bonding pairs of electrons. That's two. Bonding pairs of electrons between the central and outside element, that's three pairs. And then between the central and outside, that's four pairs. I don't have any more pairs of electrons. I'm going to verify the duet rule for hydrogen. Yes, that's a duet. Hydrogen duet, yes. Hydrogen duet, that's a yes. Hydrogen duet, that's a yes. And silicone, all other elements, that's 2, 4, 6, 8. That's an octet. Bingo! We are done with that one. Now what we're going to do is we're going to draw out the ax. So A, X, E. So the central element is the A. That's the silicone, and that's an A. The outside elements in the positions of 3, 6, 9, and 12 o'clock are the X's. And how many of those do we have? 1, 2, 3, and 4. Do we have any lone pairs on the central element? That's a no, so we actually do not do that. So now we have AX4. If we look at our table here, we're going to find AX4. We have highlighted that on a previous video. AX4 corresponds to the name of tetrahedral. And that is what we're looking for. What is the bond angle for tetrahedral? 109.5. 109.5. Perfect. And then we got to draw that, make that model and come up with what it is for us to get this one. So we're going to do that. And on my sheet of paper, it says the following. I don't find silicone anywhere on my sheet of paper for my key for my model set. But, however, what you should see is that carbon and silicone are in the same group, in the same column of the periodic table. And so here's why you should see asterisks on these. Asterisks can represent any element within the same group as well. For example, the black can represent silicone and the green can represent fluorine, bromine, and iodine. So that means that that black one represents not only carbon, but anything within that same group, and silicone is in that same group. So therefore, here is the model for silane. And you see that black one represents the silicone in this one, and the white ones are the hydrogens, okay? And the tan ones are the bonding pairs of electrons here, okay? This is the bond angle of 109.5, and that bond angle goes everywhere within this molecule here. You should see that every single thing that I'm touching here with my fingers, they are the same. So that means that this is symmetrical. So on the outside, everything is the same, and that is symmetrical, and that is non-polar. And let's go back to the water molecule. If I were to touch these two things and the lone pairs, so that's what's critical here. If I were to touch these hydrogens and the lone pairs, I'm touching different things. That is asymmetrical. If I go back to the first one, hydrogen sulfide, if I touch these hydrogens and the lone pairs, that is touching different things. That is asymmetrical. Polar. If I go to the ammonia, if I touch these things right here, then I'm touching different things. That is asymmetrical and polar. Perfect. We got one more to do, that's phosphine, and I've written down the structure for you for that, or sorry, the formula rather, that's pH3. So first thing that we do is we look at our periodic table, we find the valence electrons on phosphorus. So how many valence electrons on phosphorus? That would be 5. So there are 5 valence electrons on phosphorus. There's one phosphorus atom here. Look, there's another hydrogen. No way. Hydrogen. How many valence electrons in hydrogen? 1. So valence electrons in hydrogen, 1. But there are 3 hydrogens within this formula here. So we're going to add these up. That's 5. That's a 3. Sum them up. That's 8. Like everything on this worksheet. Divide by 2 and you get 4 pairs. Notice that this worksheet, everything has 4 pairs on this worksheet. That won't be the case for every single one of the worksheets. The least electronegative element goes in the middle, but never hydrogen. And so that means that phosphorus goes in the middle. And then we're going to do X marks the spot, sign of the cross, and that's where the other elements go, in the 3 o'clock position, in the 6 o'clock position, in the 9 o'clock position, and I've just run out of elements, so I can't place any more. Erase those dashed lines. It's just as a reference. And then I'm going to follow the set of rules in placing electrons. And so the first rule is placing bonding pairs of electrons between the central and outside. That's at the 3 o'clock. Central and outside bonding pairs of electrons. Central and outside bonding pairs of electrons. I used up 1, 2, 3 of my 4 pair. My next rule is to place lone pairs on the outside atoms, of which I cannot do for hydrogen. Then the next rule is to place lone pairs on the central atom, just like that. I'm going to verify the duet rule for hydrogen. That is a duet. That's 2. That is a duet. That's 2 for hydrogen. Duet 2. Hydrogen is the only element which follows the duet rule. All other elements follow the octet rule. There are some exceptions, but we've got 2, 4, 6, and 8 electrons. That's perfect. I'm going to end right there on that one. But then we have to do the AX, so AXE. We could erase all that here if you want to make that look nice and pretty. I'll just leave it there for the moment. So AXE, the A is the central phosphorus. That is the A. There is always and only one A all the time. Then the X's are the bonded elements surrounding the central element. There's 1, 2, 3 bonded elements to that central element. So that means that there are 3 of these. The E's are the lone pairs on the central element. So that is this. Now notice, 1 E represents 2 electrons. It's a lone pair. It's a pair. It's not every E is every electron. No, 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 no. It is a pair of electrons is a single E. So if I go back to the water example, that's why there are 2 E's, because each of these lone pairs is represented by 1 E. Okay, just making sure. AX3E corresponds to a name of a shape, so that's why you need my handout here. AX3E corresponds to trigonal or trigonal pyramidal. So trigonal, pyramidal. And what is the bond angle for trigonal pyramidal? AX3E, trigonal pyramidal, has a bond angle of 107 degrees. And is this polar or nonpolar? Well, we need to make the model, but it is also right here as polar. So this is polar. And that means that it is asymmetrical. Make sure that it is asymmetrical for polar and symmetrical for nonpolar. Okay. So we're going to make the model, and just like before, if we look at our key, okay, we are looking at this 4-hole nitrogen here, and nitrogen and phosphorus are in the same column, so I'm going to use the same model for the nitrogen and for the phosphorus. So that's why we have the blue one, which is a nitrogen, but it also represents the phosphorus, because it's in the same column on the periodic table. All right, so the bond angles here are 107. These are 107, 107, 107. Those are the bond angles here. And so this tan thing represents that lone pair of electrons, and that is most certainly asymmetrical. That is, if I touch these things, I'm touching different things, and that is asymmetrical. All right. So just let's zoom on out here and so that we see the entirety of this worksheet and everything on it. And so you should see all those. And then so all the models that we have done here are as follows. You can see all of these in their different shapes and forms. All the models are right here. Oh my gosh, so many models, so much information. I hope that worked out real well for you. I hope you have a fantastic day, and I will see you next time for the next video. Bye for now.